Once we understand the relationship between a function and derivative, we've got to apply it to sketching the shapes of curves. This particular example here is a parabola we can see. F of x equals x squared minus 4x plus 5, and we want to have a go at sketching what this graph is going to look like. This example is a little bit different to previous types of problems that we might have met, and the reason is this actually does not factorize. So often when we were sketching these things, we'd want to factorize it and find the x-intercepts. If you actually try to do that, you'll see we're looking for two numbers that multiply to give positive 5 and that add to give negative 4. You can work out pretty quick that there are not two numbers that will do that. So this is not factorable. And what that means is there are no x-intercepts. Okay. And that can make it difficult to sketch if we don't have derivatives to work with, because we really don't have many features we can mark on. There's no x-intercepts, so it means it's going to be somewhere up here, or it could be down here. We don't know yet. We've got to work that out, but we're not going to be cutting the x-axis anywhere with this graph. So let's take the information we can get out of this. We know that all polynomial functions have an a y-intercept given by the constant term. So the y-intercept is equal to 5. So it's got to cut here on our graph. Now, that's good. That tells us it's going to be some kind of parabola going this way. Of course, we could also have told that by looking at the x squared, and the fact that it's got a positive coefficient means it's got to be concave up, which means it has to be above the x-axis if it doesn't have x-intercepts. But that's helpful. Okay, so we've got one point that the function has to go through. The other thing we really want to get is the turning point, and we're going to use our knowledge of derivatives to do that. So I'm going to take this function, and I'm going to differentiate it. So here I'm going to get 2x minus 4. Hopefully that's relatively straightforward. And we know that turning points occur when the derivative, I don't know why I'm writing derivative, I can just use f dash of x, is equal to 0. So to find the turning point, we are going to set this expression here, 2x minus 4, equal to 0. In other words, we're asking this function, what x value makes you equal to 0? What x value gives us a turning point, a place where the derivative is 0? So now we solve this equation, and that's a fairly straightforward process. I get that x equals 2. So somewhere on this x equals 2 line, the turning point is. So it could be down here, it could be, up here somewhere. We don't know. We got to get the y coordinate that goes with this x, and we can easily get that by just substituting into the function. So I'm going to work out what f of 2 is. I can't remember the equation off the top of my head. 2 squared minus 4 times 2 plus 5. And I get 4 minus 8 plus 5, and that will be equal to 1. So that means my turning point has to be here. And once I've got that, I kind of have enough information to sketch this graph. I've got as much as I'm ever going to get. I know it's got to have a y-intercept here, and it's got to have a turning point here. The symmetry tells me it's going to also have to go through here. So that should be enough to get a decent sketch. I'm working on a tablet, so my sketch isn't going to be amazing. But it should look something like that. And I should mark on that this point is 2, 1. And that is how I would sketch the graph of f of x equals x squared minus 4x plus 5.